want to welcome everyone to the AIMEDx webinar. We are super excited to host Professor Philippe Schwaller. So Philippe is a tenure track assistant professor at EPFL, Switzerland. He received a bachelor's and master degree from EPFL. While working for IBM Research, Philippe completed a master degree at University of Cambridge and a PhD degree in chemistry and molecular sciences with Raymond's group at University of Bern. In February 2022, Philippe joined the EPFL as a faculty at the Institute of Chemical Sciences and Engineering. He is currently leading the Laboratory of Artificial Chemical Intelligence, which focuses on AI-accelerated discovery and synthesis of molecules and materials. Philippe is the co-PI of the National Center of Competence in Research, NCCR Catalysis, which is the Swiss Center for Sustainable Chemistry, Research, Education, and Innovation. He received many awards, including the QCMS Punch Awards, the Lattice Foundation University Award, and the Novartis Early Career Research Award. So, Philippe, we are super excited to have you, and welcome to the AIMEDx webinar. So the virtual podium is yours.
Thank you very much for the invitation. It's really a pleasure to be here. Hope at some point I'll be visiting you in person. And you probably all know that in chemistry and material science, we have a nearly endless space to explore. If we only focus on like drug-like molecules, there are plenty of estimated numbers, but one of them is 10 to the power of 60. So in my lab, we're exploring like kind of how we can use AI and machine learning to accelerate the molecular or materials design cycle from what molecules we want to make with applications, mainly in catalysis and drug discovery, always keeping experimental validation in mind. Although we are a purely digital lab, almost every of my PhD student has a connection to an experimental group, or we have plenty of more experimental partners in industry to like how to make those molecules and materials because they're actually not this is often a bottleneck that we kind of have to overcome if we really want to have some gold standard validation. So with applications in synthesis planning and synthesis optimization. And today I'll show you some stuff we do with very small language models, for example, for de novo design, to large language models used for chemical research. So what I mean by language models, and probably I don't have to introduce that to this crowd, but I kind of, if you just take a general purpose language model, such as is behind ChatGPT, then it's trained on the whole internet up to a specific cutoff. And if you imagine a model that was trained on everything that existed before today, maybe like kind of if it was trying to predict the next token or word, then it would predict something like Philip should prepare slides for his AIMEDx talk. And in chemistry, we can kind of also train such models, but we typically do it to predict like the next part of the molecular graph, the next atom, and stuff like that. And to do that, we need text-based representations. And we're super lucky that back in the 80s, someone developed SMILES, and you can see an example here of how this molecular graph here can be written in text, where you have different characters for the atoms. You can describe branching, ring opening and closing, and also some limited stereochemistry if you want to. And yeah, long before the long before somehow it skipped, yeah, long before like kind of ChatGPT came up, I was already working on language models for applications in chemistry, for example, reaction prediction, where we had introduced the first transformer applied to somewhere in chemistry, where we would just translate from reactant molecules to product molecules and learn this translation function. But let me start with something that is a bit simpler. If we want just to teach a language model to generate molecules, what we would typically do is define a pre-training data set, go to one of the big data sets that exist, for example, PubChem or Campbell, take them the molecules as mice, and then similar to how you would train GPT on natural language text, basically learn this distribution of molecules with the language model. And this language model would now know how to sample molecules that are similar to this pre-training database. But often this is not what we want. We have kind of a specific desired property profile in mind that we would like to have, and we would like to steer this generative model towards that. And to do so, we start with the pre-trained model, and then we enter kind of a generate or sample. We sample the model, we calculate a score that basically tells us how close we are to the desired property profile. And then based on the feedback that we get from that score, we kind of update the model. And this can be done with reinforcement learning. And the tricky part here is often the scoring, because scoring and labeling those molecules can be very expensive. And what we worked on with Jeff, who just recently defended his PhD, is how can we be as sample efficient as possible. So uh, if we define one sample and one oracle call as a computational prediction or simulation, then sample efficiency is how few labels do we need to add into this or do we need to explore to basically bias the model towards a region of chemical space that is interesting. And sample efficiency is super important because often when you have this desired property profile in mind, you want something that has not existed before. And they're like kind of easy to train machine learning model on everything that has been seen before are usually quite weak because you push them out of distribution, and those generative models are usually quite good at exploiting any weakness in your oracle. And so people try to go towards more physics-based simulations and more costly simulations. And the more sample efficient your models are, the better the simulations, the more accurate the simulations that you could kind of take into consideration in that loop. If you look at what we've done in that space, one of our first publications was augmented memory. This was really kind of based on reinvent, but we kind of thought about what are all the different ways how we can reuse the sampled information, like by augmenting the size, having, yeah, caching the oracle calls and so on, and like really kind of never lose that expensive information. And if we compare results on the PMO benchmark, practical molecular optimization benchmark, where for once in a this was a benchmark where there was a limit put on the number of oracle calls that you could have during your optimization. We see that often big like approaches that are super fancy and published at big machine learning conferences, they are not super sample efficient. They sound super nice, but kind of if they are limited in the times they can be called the oracle, they're actually not that useful. And reinvent as well as augmented memory back then were topping that list and were LSTM based, so like a super simple language model. More recently, we had some successes with the Mamba architecture, which is a safe space model and kind of, yeah, uh, where we could show that on more challenging multi-objective optimization, we could further increase like the sample efficiency. And now we are getting to like ranges, so depending on the task, like with less than 100 Oracle calls, we kind of find the first promising candidates, and we typically get like it really also depending on the task, like 300 candidates for 1,000 simulations. I just want to provide you kind of one example that kind of fascinates me in not in drug discovery but organocatalysis, where basically we try to explore like what would be good organocatalysts for the Morita-Baylis-Hillman reaction. And for that, the Jensen group in Copenhagen had published a physics-based oracle. They had some successes. We quickly like realized that when we tried to optimize their oracle, it was not strict enough. Like our models were too powerful and would really find like kind of would hack the original oracles, and we improved the oracle and kind of entered in such a goal-directed learning loop, really from smiles to like physics-based scoring back to the model. And what we could observe is that this is just one example of a design catalyst, is that although we were kind of like generating in 2D and only smiles, like those models were strong enough to almost perfectly capture like 3D functionality, and design bifunctional catalysts where they would place kind of okay, they required amine but then a rigidified linker and a hydrogen bond donor on the other side that would actually stabilize the transition state. And I think for me, this was like kind of an unexpected thing, because there was this constant debate of whether you would need 3D models to kind of actually do similar things or not. And it looks like language models can also learn that. I'm not saying that 3D models are not good, but it's just a surprise that we can push language models in that way. And I think like the results were exciting enough for experimentalists to then go on and try to synthesize them. And then the whole mess started, because, yeah, synthesizing those molecules, even if they look quite feasible, is not always straightforward. And kind of, I would say, in this whole field, synthesizability is kind of a key bottleneck. And that's why, like with Jeff, also we thought about how could we actually make molecules that not only fulfill like the basic properties we want them to have, but are synthesizable at the same time. And there are plenty of approaches that go more the bottom up route, where like kind of you take some building blocks that are available, you put them together with a reaction, and like that, you kind of design your molecule. We said, like, why can't we just take the same kind of general smiles generator and then kind of add the synthesizability, or like kind of a retrosynthetic model somewhere in the objective? And we could show that we could also get if your model is sample efficient enough, then you can also add that, and you can, within like 1,000 oracle calls, you kind of find things that not only optimize the docking score and 3D and SA, but also where a route is found to like commercially available building blocks. What we can additionally do is to not only enforce the kind of the actual route, but the next step is kind of to say, hey, but maybe we have some specific starting materials that we want to work with, or you could imagine you have bio-based building blocks, and you would like to have, I don't know, 50% of all your atoms coming, or carbon atoms coming from a bio-derived source. You could say, I want to improve specific hits, or just that the lab could at the moment only have those kind of building blocks available. And to do that, you kind of this is super challenging because now you want to have quickly find some candidates that optimize the whole property profile, have a route, and only some specific building blocks are valid to actually kind of give you a signal on that route. And uh, to kind of make this possible, Jeff had to come up with a new reward function that we call Tango that would kind of measure Tanimoto similarity and substructure match from the different nodes in the route to the actual enforced building blocks to kind of, but yeah, once we had that, we actually had different case studies where we could constrain the generation to at least include one of the building blocks that we defined in this typically set of 20-ish building blocks. If we At the moment, we talk a lot about automation and kind of how we could accelerate chemistry, because here you are still having like lots of possibilities that might be outside what your robotic platform can do. So how can we facilitate synthesis even more? And enforced building block we had, but we thought that if automation platforms are typically good at very specific reaction classes that can easily be automated. So we would also like to enforce further constraints like on the reaction types, or like say avoid specific reactions or minimize the steps that kind of all those molecules get more accessible in the future. And in a recent preprint, here's just the reference, we are kind of pushing in that direction. And we have case studies where we say, hey, if now we started with just the building blocks that are available by NME and can be shipped within a week, then what we also want to do is revalorize some waste materials that we have in Europe. So we also do the same example with the US stock and US waste material, but that's the one I have on the slide right now. Then we want only to use our favorite reactions. We want to have mi bond formations and maybe Suzuki couplings, because we know that we have a high success rate when we perform those. We can actually now, with a reasonably limited kind of number of oracle calls, find routes to molecules that basically, yeah, fulfill all those constraints. And kind of yeah, I think like kind of the 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 big challenge now is not really the generation of molecules anymore. I think like I've always shown to you like language models, but we have also plenty of good extremely good generators in the 3D space. It's more about how do we actually develop more realistic scorers, because in plenty of the kind of studies we ran, often when we then go from our like ideal computational world where like everything looks nice to actual the real world where chemists synthesizes those molecule and tests them, then very often the results still look completely different, even though the computational score were amazing. If you're interested in more on that topic, I can point you to this review that we've written a bit more than a year back. I think like one of the most useful things in that review is really the table where we made sure to collect every single like de novo generation work that was experimentally validated. And what is kind of cool, there's also this link to Jeff's GitHub repo where he continues to collect those. So this is an outdated list, but now there are already more than 70 studies on Jeff's repo where there was some experimental validation. Maybe some of you are more into the material space, and kind of that's why I thought I would also include some work from Junbu in my group, who is now not working with language models, but the generative model is a diffusion model, and this can be more or less any. We basically built a pipeline that is not dependent on the diffusion model. Typically, we use MatterGen, but you could replace that with another one. And there you kind of generate 3D structures of crystals with different flows on lattice atom types and coordinates. And what we kind of where we did the work is adding the goal-directed reinforcement learning pipeline on top of the diffusion model to actually fine-tune that to spaces of interest. And what we can show, and we have an old outdated preprint somewhere on open review, but we'll soon, hopefully next week, put a preprint on archive, also pointing to the code and everything, is that we can actually, with a reasonable DFT budget or MLIP budget, typically like roughly 500 additional labels, we can optimize for single properties and a wide range of that. You have kind of, we have even more use cases in the preprint, but from band gap, heat capacity to magnetic density, and kind of using a very similar loop as we do in de novo molecular design. You might wonder what's the benefit of that, and let me just show you one comparison to MatterGen. MatterGen, when they kind of want to like use conditional generation to design a new material that has a specific band gap, what you typically do is you pre-compute labels on either 40,000 or 600,000 materials, and you have to label all of those with DFT, for example, and you're kind of uh, and then you can start this conditional generation where we start with the base model that is not conditioned on anything, and we, in this reinforcement learning loop, we kind of try to only label the materials that actually give us more information and kind of help us to bias the model towards the properties of interest. And we can show that, for example, on magnetic density, where we can kind of, after like the fine tuning it on those 1600 materials, we can basically shift the whole distribution of the sampled materials, sampled crystals, exactly to that kind of value that we want, and also for band gap. And this is really like kind of, this is after conditional kind of the conditional fine-tuning of MatterGen, and after our reinforcement learning pipeline, like how many of stable, unique, and novel materials we are able to sample with a limited additional DFT property budget. And it looks like a much more efficient way of doing that. We can also go to multi-objective, and kind of this was, I think, also something that we could compare with MatterGen, and try to design permanent magnets with low supply risk. And we can kind of show how the model, with like the different loops that you see here, like kind of comes closer and closer to the desired property values. And here are just some examples of the designed materials. And again, like kind of, we don't need to pre-compute DFT labels to actually be able to push the model into that space, but it's basically on the fly tagging more materials, requesting DFT calculations. And yeah. But let me switch back to my original topic and let's go back to large language models, but this time like general purpose large language models. And you all know, like 2 years ago, when you were querying ChatGPT and testing that out on your favorite, more scientific question, they would confidently hallucinate. And now they're a bit better, and they have like typically you see on the platform, you have also the web search that you can activate or the deep research function. They're basically what happened in the last 2 years is that we gave language models access to tools, and that kind of are meant to reduce hallucinations and solve different tasks better. And even before GPT-4, we kind of started exploring that for chemistry, augmenting LLMs with chemistry tools, and GPT-4 really the kind of the access to that then unlocked some even better use cases. And but like kind of we gave GPT-4 access to 18 different chemistry tools, and we called that agent ChemCrow. And yeah, let me just highlight Andrew, who is now at Future House, but this was a collaboration with him. And I just give you one example. Like if this was in the paper, we have one of the first kind of demonstrations from prompt to actual synthesis of a molecule, and there the task was design and synthesize an insect repellent. And the language model could really go, okay, ask the question, what is an insect repellent, query the literature for common insect repellents, get a few options, including DEET, then select DEET, but this didn't contain any structural information, so it's just a common name. So it had to use the name to smiles tool to actually convert DEET into this text-based molecular representation, which was then compatible with synthesis planning tools that I developed during my PhD. So we could get back the recipe of DEET, and because we connected it to a robotic platform at IBM Research, we were actually able to execute that synthesis. So like after human confirmation, the language model like run synthesis, and after 2 hours we were able to confirm that DEET was actually synthesized. The I think ChemCrow is a wonderful proof of concept and demonstration of what was feasible, but kind of there's in this line of AI scientists, it's still a lot of the papers are kind of trying to fish for the actual use case where kind of you can show something, and they're not always necessarily super robust pipelines. They work very well in everything you show in the paper, but kind of the a lot of the time I think we aim also for maybe things that are too general, and there's always someone that will find something where it breaks. Uh, I was the point I want to make is evaluation is extremely challenging, and together with Kevin Jablonka, and this is really led by Kevin Jablonka, is we kind of thought, how could we fairly like at least get some hints of which LLMs are actually good at chemistry, and we developed ChemBench by extracting multiple thousands of multiple choice questions from university exams or chemistry olympiads and other sources. And what we could see already back then is that those some at least the commercially available LLMs were already quite good at answering chemistry questions correctly. And but I'm always wondering, yeah, it's okay that they are good at chemistry questions, but is this really what I'm caring about? Because like kind of is a language model that is good at answering those really useful for me to do research and accelerate discovery? And one recent work we did is more going towards retrosynthesis. Retrosynthesis, as a quick intro, is you have a target molecule, you want to find back commercially available building blocks, and you want to do that step by step backwards until you know the complete route. And there are plenty of solutions available. Also, kind of if you take, for example, AI Zin Finder from AstraZeneca, but I think like there's not a global adoption of those solutions because like kind of there's still like if you show a chemist like 10 routes that come out of such a program, they will quickly find some major mistakes and basically say, hey, your AI tool has not really learned chemistry, and this yeah kind of no yeah. So how can language model help us with this challenge? And what we observed is that kind of whenever we would query a language model to generate a molecule or chemical reactions or reagents and reactants, they were not that good. They're still kind of weak with smiles, at least the majority of them. But whenever we would show them a molecule or a reaction to comment on, the reasoning in plenty of the cases made a lot of sense. So what we thought of is to combine both, like kind of a more traditional ML algorithm to predict synthesis routes and plenty of options, but then the language model to actually see which options align with a human query, a human expert query, where you can kind of define plenty of requirements that you would like to have. For example, break the pyrimidine ring in early stage, but get all other rings from commercially available building blocks, and then kind of we have a system where basically the language model looks at plenty of options and rates every single route to basically tell you re-rank which one matches those requirements the best. And we tried this on multiple targets with multiple different queries, and this is just to give you another kind of example where it's kind of really catches a fine-grained change in two synthesis routes and scores one much higher than another. But the point I really want to make is on this benchmark, GPT-4 2 years ago, basically just no, like kind of no score at all. And now we've seen really with Claude 3.5 and DeepSeek and also Gemini 2.5 Pro that language models are getting better and better at chemistry tasks and understanding kind of organic chemistry. So how can this be used? So I think we have this platform. It's at the moment, I think, still internally, but you can connect whatever your favorite retrosynthetic tool is. You can launch that retrosynthesis and then just add a steering prompt. How you would like to what you would like to see as kind of outputs, and then you can re-rank your different suggestions by the model according to your query, and you get really a detailed analysis of every single reaction step and then an overall assessment. And I think this is kind of super beautiful that we have something like a bridge from your AI machine learning model to natural language, because it kind of enables chemists to talk in their language with machine learning tools. One cool thing that we had in one revision of that paper is a reviewer was asking, yeah, but if I'm not an expert chemist, how can I make use of that approach? Because it's kind of maybe I don't know where I want to break what. So what we thought of is that we could also just mention as a strategy general feasibility, like just provide me a route with overall high yields, consider side reactions and byproducts, avoid unnecessary reaction, and provide this as steering prompt. And what we can show is that looking at the outputs on 4 hard targets for like an open source tool and 2 commercially available tools, we can basically we're able to fish with our feasibility score which of the routes are actually feasible compared to the unfeasible one. And here we exactly see the problem or the challenge with open source tools. They still produce a lot of really unfeasible routes. And that's why typically when you just look at 10 routes, you quickly find a few that make no sense, and you're kind of you're not trusting that model anymore. But if you have such a filtering step, you can just show the highly feasible routes to an experimental chemist, and this could be a way to actually kind of get a bit of more trust in those tools. And yeah, I don't know how this is too much text, but it basically tells you that like the comments it does on individual reactions and the overall assessment make chemical sense. But what I also really like is when you provide it with a route that makes absolutely no sense, it can be as harsh as a synthetic chemist and basically say, hey, those are all the steps that have key deficiencies, and even comments like it reads more like a malfunctioning algorithm output than a human desired synthetic plan. I kind of it's just wonderful to read and see that we can really those models are able to distinguish between good routes and bad ones. So now for the last few minutes, kind of you have your ideal molecule designed, you have a synthesis plan, but still you will need some optimization of all the different steps, or we face like kind of optimization problems all over chemistry, from processes to individual chemical reactions. And one go-to work on or go-to approach is Bayesian optimization, which was definitely popularized by this amazing publication in Nature a few years back. But yeah, whenever you have a new reaction, I kind of, there's always the question, what kind of descriptors should I use? Chemistry is not like this simple thing where you can just represent everything with a float number, or like kind of or where you have very clear classes. There are so many representations that exist, and there are the people that tell you DFT descriptors will provide you with like the best information. But then even then, like kind of what do I compute my DFT descriptors? Which one do I select to reduce the space a little bit? We're in the low data regime. We have no way to like kind of actually validate that, at least if you do it in a prospective way. So we need a solution for that. And Bojana, who is more from the computer science in my group, she thought that, hey, why don't we represent everything as text? We can either represent the smiles as text or have simplified procedures. We can encode whatever we want in there. We pass it through an LLM. We get a representation. Luckily, we are kind of not fully computer scientists, because if we were, we would have said, but it's impossible to optimize in 700 dimensions. But we like kind of did this high dimensional optimization using LLM based embeddings. And 1.5 to 2 years back, we had initial results, but they were really bad, because like the best chemical features were a lot better in finding kind of the top performing points in chemical reaction data sets. But more recently, we managed to jointly train the LLM, not use like fixed embeddings as we did previously, but jointly train LLMs and the GP, the surrogate model for in our Bayesian optimization loop, through path using the LLM as a deep kernel. And just to kind of show you again, like kind of we would have an LLM input describing with a simplified procedure for the reaction, a target, and really during kind of the retraining of the surrogate model, we basically passed the marginal likelihood gradients of the GP back through the LLM and continuously adapt the embeddings to match better what we observed in the new data. And to make it extra hard, we kind of, in all the experiments I show you, we go to only 50 sequential data points, and we start with 10 failed experiments in the data set, which means we randomly select 10 experiments below the median. And what we can show is we kind of optimize that on a Buchwald-Hardwick reaction data set. We can show that the approach we developed is robust to input formatting, so we don't really care whether we represent the reaction as smiles or just a basic reaction setup. We also don't need necessarily to have chemistry pre-training in the LLM. It's LLM like T5 models that are either trained on general knowledge or on chemistry knowledge perform the same. We made it robust to architectures and hyperparameters. Means we have a single set of hyperparameters that we use optimized on one data set that we use across all the experiments, and it works for here you have encoder decoder models, you have decoder only models, and you have encoder only models, and we benchmarked it on 19 different tasks, and on average we're kind of we have the best performing approach, better than traditional GP like approaches with chemistry based descriptors that change from data set to data set. Here we just have a general approach for all, better than just fixed LLM features and other LLM BO works that not do not jointly train the LLM and the surrogate model, but have like kind of a separate training for the LLM and the surrogate model. What is kind of cool is that we can really see this adaptation of the design space throughout the iterations, and we kind of see also here this more or less the same thing, but we see how kind of the distance between high to high points and low to low points becomes closer, and there's like kind of they're moved further apart, and this is kind of on the underneath you have fixed LLM embeddings versus the adapted ones, and uh, I think like kind of the intuition is that it's much harder to optimize on a space that is a lot more messy and noisy than if you kind of fine tune your LLM embeddings at the same time. You kind of put through the GP marginal likelihood objective function, you kind of put points that are high yielding closer together and points that are low yielding further away. And this kind of has also a very positive influence on the LLM embeddings. And what we can show in terms of predictive performance, where those models kind of learn the task quite nicely, but they also keep the uncertainty quantification more or less in the same range as you would get with a GP on more chemistry relevant features. You're kind of almost like penalizing the NLPD measures penalizes kind of, if in some sense, hallucinations where you have confident wrong predictions, and I think this is a nice outcome. And yeah, everything can be represented as text, so I think like Golem is a super interesting approach to try, and we already have some follow-up work in the pipeline for that. So stay tuned, and in hopefully a few months we will be able to show you more exciting stuff. If we combine all of that, we can kind of think of this vision of this AI scientist, and maybe have a system that generates ideas, scores them not only for novelty but also feasibility in your current kind of platforms you have available. You could run experiments, analyze the results, and hopefully find the best experiments together with like kind of so detailed report in a more automated fashion. But yeah, I think like the goal is really to augment human capabilities in all we do. So today you've seen more the small language models that design like kind of new molecules, or the diffusion models that we fine tune in the low data regime to generate kind of novel materials, then large language models for chemical research. And because this low data regime is super important in chemistry, how we can basically use large language model somewhere in a BO loop, starting from nothing, more or less, besides a description of the actual problem. With this, I would really love to thank my team, because kind of I'm super fortunate to work with brilliant students and postdocs, and I couldn't be presenting today without like kind of all they do, and amazing funding that just trusted me early on and kind of invested in a risky young researcher. And thank you very much for your attention. Happy to take any questions. Thanks a lot.
Thank you, Philip, for the excellent talk. There's many exciting ideas. So for attendees, if you have questions, feel free to drop it into the Q&A box. So Philip, I will read out the questions, make sure everyone can hear it.
Yeah,
So
I don't
so
see the questions, so you can.
oh, you don't see that? Oh,
Yeah,
okay, I
okay,
can see
because I
it.
have nothing, like kind of, I only see your face basically
Oh,
on
I
the screen
see.
from Zoom. But
So
yeah,
let me read it out. The first question is asking about tools
yeah.
used in the language model. So if, for example, you use to run a MD simulation with a language model, you
Mm-hmm.
still need a good wrapper of Amber GRAMAX to run it after language model understood your prompt. So at the end, the goodness of your MD simulation would depend on how you write the wrapper, as it was before the LLM. Is that the case?
We have we have some work. Okay, so basically, in there was a recent hackathon in the LLM for chemistry and materials space, and some of my team members actually played around with like building an agent for MD simulations. And there's also MD Crow, I think, from Andrew White. You can definitely get a lot of inspiration there, but I would say just yeah, I think like you definitely need the tools and well-written tools on top to facilitate or what the language model has to do. If you don't, I guess you will get some successes and some failures, and it will not be a super robust approach. Even if you have very well done tools, the I think like one weakness of those language models is that they are quite stochastic, and even
Mhm.
with the same prompt, you sometimes get quite different answers, at least if it's somewhere that kind of is a bit more out of distribution. Like kind of you will have more diverse answers possible, and kind of yeah, super nice when it works. To get the robustness that is actually useful is needs a bit more thinking about how you wrap everything, and you put some checks inside, and what you do whenever you have an error, either in code or input file, and so on. Yeah, but
Mhm.
yeah, definitely
Yeah, sure.
possible. Getting the
Mhm.
required robustness is a bit more challenging, but definitely feasible. Yeah.
Mhm. The next question is from Aditya. So you mentioned constraining molecule generation to specific building blocks or reaction types.
Mhm.
So how does that constraint affect the diversity and the creativity, I guess, novelty of the generated candidates?
That's a very good question. I think like kind of in the end, I think like there's always a huge trade-off between like constraint, sample efficiency, diversity. I guess like kind of you, yeah, often the more sample efficient models are kind of produce less diverse molecules because they're kind of good at whenever they have like the really first successes, like to kind of focus more in that chemical space. Then you have like kind of you have diversity filters that you can include that pushes them away again. But like kind of in general, I think like kind of yeah. And you also see that the more constraints you put, it might sometimes not be possible to get the top candidates that you had without any constraints. But I think this is clear. But I think in often when we do that, it's really with a practical mindset, like that we want, what do we care about? We want like kind of to have a few molecules that have a score that is somewhere in our property profile that we deem to be good enough, better than
I
kind
see.
of,
I see.
and
Mhm.
we do not care too much about having the an as diverse set as possible. We just
Mhm.
want to experimentally validate 20 of them, and we want them to
Mhm.
be feasible and nothing
Mhm.
else.
Yeah.
Kind of, I think this,
Yeah.
but it's a completely valid question, but
Yeah.
it goes a
Sure.
bit against maybe typical metrics that are used for those models and
Mhm.
that want to maximize diversity. Yeah.
Yeah. Thank you, Philip. Another question from Jacob. So what training data do you think Cloud and the other latest language model are training on that has improved their understanding of chemistry so significantly?
This is just a wild guess. I don't know. I kind of because am I actually allowed to comment on that? No, I don't know. But I would guess that okay, they had certainly like a huge effort where they tried to digitalize a lot of textbooks and things like that. I would imagine that Google internally has. A lot of access to books. I don't know what they put. For me, no way to tell you what they put in their training data, but I can imagine that they just have access to plenty of non-open data. And then I think
Mhm.
like the other, okay, what is what I would say how we can basically steer what they will be good at next is basically by putting benchmarks out because kind of now that Chembench is online, it's certainly integrated somewhere in the validation pipeline of those large language model providers. So they kind of get a signal. They get like, do we improve on ChemBench or not? This is one of probably thousands of different benchmarks that they run internally while developing the models. But having that signal makes them care about being better in chemistry. So with every single benchmark we kind of put out there that kind of is related to our field and somewhat accepted by the community and potentially added in those validation pipelines, we kind of give them some kind of incentive to become better at those tasks. And yeah.
I see. So next question from Bell. So is asking if language model can already speak chemistry language for molecules. So have you ever tried to do similarly in teaching the model to speak surface chemistry, like in hydrogen catalysis?
So far, like kind of I have a YouTube and kind of I'm showing in that talk, I'm showing mostly like the language model stuff. I think with Junwoo and Edwin and a few others, we also look a lot into more like sometimes still a bit with language model, but we kind of incorporate also simulations and so into the whole thing. I think like kind of there's definitely potential. It's
Mm-hmm.
maybe not as it's kind of maybe a bit more challenging to describe in language and to automatically like kind of even as a human expert kind of tell you whether the generated description makes sense or not. And I don't know, like kind of I think it would require a bit more thinking about how what question to actually ask and what where we could have an outcome, yeah, that we could actually measure and
Mm-hmm.
yeah, but I think like kind of
Yes.
would be super nice to explore. Yeah.
Mhm. Yeah, I accidentally skipped one question from a teacher. So will data-driven model make DFT descriptors obsolete, or do they still add physical insights?
I will not say obsolete and kind of this is I think DFT descriptors and DFT simulation. I think there the bottleneck is how do we make a pipeline that is general enough that you can do something else than just explaining experimental results, but kind of push towards new spaces and still get something useful out of that. And but I think like we're often trying to have like a physics informed step somewhere inside the whole loop because it's
Mhm.
super useful, but kind of you yeah, yeah, it's just how do you best combine that and how do you
Mhm.
kind of get pipelines that are robust enough to
Yeah, yeah,
cover
totally agree.
more than just the kind of all the results I see in DFT that is often like the results experimentally were already there and they're kind of used to explain those experimental results and there you can always tune your DFT computation to make it shine and
Mhm.
make it match but yeah we have some projects going on where we do like some computations where we actually kind of try to do more prospective predictions of what could be an actual change to the system that could kind of lead to a better reactivity. But this is ongoing
Mhm.
work, and I think it's super. Yeah, even like kind of
Mhm.
you enter into so a space of like what's the correct conformer or like conform ensemble and kind of while
Mhm.
in data-driven approaches you're kind of often skipping over all that and saying yeah my smiles kind of represents this conformer ensemble and we anyway it would be hard to define what is the correct one.
Yeah, yeah, that's right. So the another question is about it is possible when metals are considered in the chemical structure. I guess asking about the metal organic complex in the system.
Yeah,
What's the
so
challenge?
Yeah, no, definitely challenges with the representations, but I think like kind of those data-driven models often do not really care too much about the representation, as long as it's better if you are consistent. But you could kind of even have, like, if you have a palladium catalyzed reaction, you can have the palladium catalyst represented as palladium atoms and then like kind of loosely connected ligands. So I don't know, like without even defining the bonding that is anywhere like kind of challenging to define. And if this is the representation you're going for and you have a set with different ligands and some kind of different output, the model will kind of just learn that the effect of changing that ligand to that will be this on your output. I think that kind of without, yeah, we're simplifying a lot, but sometimes this is maybe the best abstraction for which we have actual data for. Yeah.
Mhm. Yeah. So the next question is more future visionary. So they're wondering if the goal of developing machines can perform as human chemists. So what's your insight and viewpoint on what a future generation of human chemists will do in, let's say, in 20 to 30 years from now?
I think it's hard to predict 6 months ahead. So no, I think like kind of the but we had different kind of revolutions in the past, and kind of every time I think the humans adapted to like use the internet or whatever that came as a next technology that would kind of facilitate like looking up similar chemical reactions and stuff like that. This is most likely what will happen is that kind of people will start using AI without even kind of realizing how they are using AI because it will just be integrated in their workflows and like that it will. But I think like kind of having the domain experts and I'm yeah, what
Mhm.
is maybe kind of also challenging is more how do we educate this next generation that grew up with like ChatGPT and kind of for every single question they have, they will just ask a language model and have the feeling that they can kind of always ask a language model. And no, I think like kind of how do you teach the next generation like to leverage language models in a way that they don't completely dislearn thinking by themselves. I don't know, but this is
Yeah.
more maybe going towards yeah, philosophical. Yeah, no, but kind of there's definitely a challenge time ahead, but I think there will be really people that will kind of leverage the tools they get to get to a next level, and there will be just the normal users that
Mhm.
yeah. Yeah.
Totally agree. Yeah. So another question is asking about if the language model already fit to select the most appropriate combinations of categorical factors for several different reaction types. If
Mhm.
that's the case, then do you know which data set are they trained on?
Uh, you, I think like kind of do you, this more probably related to the BO project, I could assume. I think like there, what we can see is actually that the most recent language models are not the best performing ones in our
Mm.
task. So that's actually super interesting because like kind of I don't think that a good language model is the one that has seen the most data and is super over converged in like a local minimum. I think like the best language model or like the best models for this kind of task are the ones that are somehow the easiest to adapt. They have general knowledge, they have seen a lot of stuff, they're
Mhm.
perfect feature extractors, but they can kind of, you can easily, like, kind of with a few data points, kind of bias towards your,
Mhm.
teach them the new space of interest. That's why, like, kind of, a lot of the best results we show in that paper are with T5, which is what, the 2020 model. So no, but like kind of it's, but surprisingly we there are now similar models that come out that have very similar architecture to T5, are called slightly differently, and were trained on probably 100 to 1000 times more tokens, and they don't work better. It's like kind of yeah, it's a question we ask also ourselves a lot. What is actually a good representation, and what, yeah, what makes a good
Mhm.
representation for chemistry? Yeah.
Mhm. Interesting. So the last question from the audience is kind of long question. So about the synthesis route.
Mhm.
So how sensitive is the model to the reaction condition when determining whether a procedure is feasible? How is the current model primarily focused on identifying plausible steps instead of independent of the conditions? If it is the latter, how does the model handle cases where the same product can be formed through the multiple feasible pathways?
I think like kind of okay, let me answer the last question first. Like kind of when you have uh, same target, multiple pathways, we're just rearranging, we're just analyzing every single pathway individually, and they're like kind of there are multiple ones that can have a very high score, and this is not a problem. Then how conditions are handled in that particular case, in like in my previous time, I worked a lot on like kind of predicting conditions together with the reactants, but the main focus of the whole field is to predict only the reactants and not the conditions, and have maybe another condition prediction model next to that whenever you define the route that you are interested in. So what we show in that preprint with the language models is all resolved on kind of routes that do not include conditions. So we're
Mhm.
just basically rating the feasibility that the transformation has independent of the conditions, and this would really be taken care of at a later stage. Then I think condition prediction is a super hard task, and there are not a lot of good data sets to actually do that, but it's definitely a challenge in the field, and there's some nice models. Yeah, yeah, no, I think like kind of, but often even if the conditions look reasonable to a human on paper, you change a solvent, there's a kind of an effect that you weren't expecting, and you have a completely different result. I think like chemistry is a lot, real chemistry is a lot harder than kind of, yeah,
Mhm.
what we make it sound to be. Yeah.
Yeah, that's great. So the actual last question just came in. So how do you model selectivity based on reaction pathways in machine learning based training?
How do we model selectivity in synthesis throughout? So we're kind of, we are modeling the selectivity of all the individual steps. If you kind of, I don't know if I perfectly got the question, but if I, from what I kind of understood, what is kind of key in our approach is that we really have kind of selectivity that is kind of analyzed on individual steps and the feasibility, and later on kind of an overall assessment that basically combines the information from the whole route and
Mhm.
the kind of the strategic prompt and basically kind of makes a summary on how aligned and how good like kind of the suggested route is, looking at all the individual chemical reactions. And
Mhm.
I think like kind of, yeah, we have
Mhm.
some work going on also. Yeah, more like kind of, yeah, bit more in
Mhm.
selectivity, but this is maybe for next next presentation at some point.
Yeah,
Yeah,
sure. Yeah. Thank you, Philip, for taking all the questions in our time. Really appreciate your time.
it was a
Um,
pleasure. Yeah, thanks so much.
uh,
And yeah,
Thank you. Yeah, I will see
yeah,
you in Golden Conference in a few months.
yes, true.
Yeah,
Yeah, I
looking
think like
forward.
yeah, it will be much more on the materials
Hmm.
related projects, but yeah, it will be super nice. Very nice.
Yeah,
Okay, thanks so
that's
much.
great. Thank
And
you. Thank you, Philip. Thank you all for attending. I'll see you next time. Bye
see
bye.
you next
See you,
time.
Philip.
Bye bye. See you.